And now we will have Jean-Marc Ginoux. Are you ready?
Yes.
Okay. Please, you can start. Thank you. So Jean-Marc Ginoux is going to talk about a physical memory store based Mususwamy Shua Ginoux system. Sorry for the spelling. So Jean-Marc, can we unmute? Where is Jean-Marc? Ah, there it is. Yes, good.
Okay, I was mute. Okay. Do you see the point?
We don't. We saw it before. Yes, we see it now.
It's okay.
Yes. Can you have it larger? Or?
Yes, it's large.
Okay.
Okay. So good morning, ladies and gentlemen. First, let me thank the previous speaker, and I'm very proud and honored to speak just after the man who has been my teacher many years ago, 20 years ago. And it reminds me all the marvelous lectures he gave us when I was a student in the Nonlinear Institute of Nice. So Mr. Coulet, Professor Coulet, thank you so much for this very interesting talk. And I really hope that you will have the opportunity to discuss again of your research and your new results of Ibn Sal and So now I will speak about a new result we have with my colleagues from Italian group made of Riccardo Meucci, Stefano Eusor, Angelo Di Garbo, and also Bharat Muthuswamy, which is from Berkeley, who was working with Leon Shah, and an Indian colleagues from called Kalya Perumal Ganesan. So first, I would like to present very quickly my talk, introduction, circuit setup, and the model, and then we will speak very quickly of the stability analysis, and we reach the discussion and conclusion. So in 1976, 5 years after Leon Shua had postulated a missing circuit element that he called memory store, he published a paper with Sun Kang in which they recalled that thermistors have been widely used as linear resistor whose resistance varies with the ambient temperature. In particular, a negative temperature coefficient thermistor is characterized by the following function. So they pretend that thermistor can be used as thermistor, as memory store. So that's exactly that we have tried to do, and we obtain a new circuit in which we involve a linear passive capacitor, a linear passive inductor, and also a thermistor, which made of a memory store. So by using the classical Kirchhoff's law, we obtain the following set of equations. Here you find again the characteristic of the thermistor, and here is the Joule's effect, as you see. And following Balthasar van der Pol modeling, we use the nonlinear for the nonlinear resistor as a cubic function, where A, B are constants. And then from both analytical and numerical point of view, let's recall that it's very difficult to investigate the previous model while keeping the exponential functions. So physically, we can restrict the thermistor to small temperature change, and hence to approximate RT by its stellar series expansion up to the second order. That's we have done. And then we have removed this difficulty. It's a numerical problem, of course. So we simplified the study of this system by posing the following variable changes, and also for the parameters, just to simplify and to de-dimensionalize the model. And we obtain what we call the Mutuswami-Shua-Ginoux system. And this system is, in my opinion, really interesting because it exhibits some very rich dynamics and some very particular properties I would like to show you now. So here you recognize the cubic function coming from Van Appel's previous works. And here it is the Taylor series expansion of the thermistor characteristics. So the stability of analysis leads to the Jacobian matrix, as you can see here. And the eigenpolynomial for Cayley-Hamilton gives a very simple eigenvalue, as you see here, lambda equal minus epsilon. And the second factor is a quadratic function, very easy to solve. So if we consider alpha as a bifurcation parameter, alpha is here, we can see that according to the values that alpha can take, we have for the fixed point two possibilities. It is either a saddle node or a saddle focus, as you can see on this diagram. And we keep all the parameters constants, and I specify that all these parameters are within the range of existing thermistors. So to investigate the effects of the changes of parameter alpha on the dynamics of the NCJ system, a bifurcation diagram has been plotted. As you see, it is very dense. So we have decided to make a zoom of this very small window here. And then we show a period doubling cascade, which is highlighted on this zoom of the bifurcation diagram. And so the transformation that can be used to have provide a better understanding of the phase space orbits. For alpha equal 5%, we have a torus here. For alpha equal 10%, we have a limit cycle. For alpha equal 50%, we have a spiral chaos. And for alpha equal 1.2, we have a double spiral attractor, which is very interesting in our opinion. So according to Ovsyannikov and Silnikov, the transition to spiral chaos along the lines of the above scenario is usually preceded by either a cascade of period doubling bifurcations or the collapse of a two-dimensional torus arising from hell, so from a stable periodic motion, so a limit cycle. This is exactly what we observe in our bifurcation diagram. A double period doubling cascade occurs, and this doubling is due to the fact that for some particular values of the parameter set, the trajectory curve take the shape of a double spiral attractor. Hence, each spiral can perform a period doubling cascade. That's the reason why the bifurcation diagram exhibits two branches for the period doubling cascade. As you can see here, one up and one low here. It's the same here. But one other feature is also interesting. The transition from torus breakdown to double spiral chaos has been highlighted by plotting the phase portrait of the MCG system for various values of alpha. In order to confirm such scenario, the Lyapunov characteristic exponents have been computed in each case. First, while using the algorithm developed by Sandry for Mathematica, and also the algorithm, the very well-known algorithm developed for MATLAB by Wolf, Swift, Srini, and Vastano, developed originally in 1984. So it confirms the phase portrait we have observed. Then, following the works of Klein and Bayer, a classification of autonomous continuous time attractors of dynamical systems on the basis of their Lyapunov spectrum, together with Hausdorff dimension, is quite quickly presented in this table. Of course, as you can see, they confirm the phase portraits that we have observed and also that we have observed in the bifurcation diagram. So the bifurcation diagram has been plotted for values of alpha between 0.001 and 12. For alpha equal 3, we observe that a multiple reverse period doubling cascade with 1, 2, 3, 4, 5 branches occurs. Such a number corresponds to the period of each spiral of the double spiral attractor. As an example, for alpha equals set.5, there are 3 bifurcation points, and so each spiral has a period 3, while for alpha equal 11, each spiral has a period 5. Let's take a look. Here, for alpha equal 7.5, here, we see 3 branches, and here for 11, you see 5 branches. And if you plot the phase portraits, you observe a period 3, and here a period 5. This feature has been highlighted by my distinguished colleague, Jaume Libre, Professor Jaume Libre for University Autonomous of Barcelona. For alpha between 2.9 and 12, the bifurcation diagram consists in intervals within which the trajectory curve takes either the shape of a double spiral attractor or an n-periodic limit cycle. So now let's switch the discussion. While using a 4-circuit element comprising a linear passive inductor, a linear passive capacitor, a nonlinear resistor, and a real thermistor, that is a nonlinear active memristor, we design a new 3-dimensional autonomous dynamical system exhibiting very particular properties such as transition from a limit cycle to chaos. Then mathematical analysis and detailed numerical investigations have been able to establish that such transition corresponds to the route to Silnikov's spiral chaos originally described by Silnikov and then by Ovsyannikov and also Silnikov, but give rise to a double spiral attractor. Another scenario leading to spiral chaos as well as double spiral chaos and also triple spiral chaos has been proposed 20 years ago by our distinguished colleague Baudin. Nevertheless, if the attractors he obtained seem to be topologically equivalent to those exhibited by the Muthuswamy-Chua Ginoux system for values of the bifurcation parameter alpha, the route leading to this spiral and double spiral chaotic attractor is different from the Z switches described by Professor Baudin, but corresponds to Silnikov's spiral chaos as highlighted by the bifurcation diagrams and also by the computation of the Lyapunov characteristic exponents. This works has been published last year in Scientific Reports of Nature and is available at this, it is an open access at this address. You can download it easily. And before concluding, I would like to mention a new article that has been published with the Italian group made of our colleagues. And I would like to say it was a great honor for me to publish with the late Tito Arecchi, who died unfortunately last year, just after this ultimate publication with us. And this is a minimal universal model for chaos, investigated originally in the beginning of the 80s by Professor Arecchi and Professor Meucci. And this is minimal universal model for chaos in laser with feedback. And we had the great honor to be in the cover. The attractor is in the cover of the previous March, the previous cover of International Journal of Bifurcation and Chaos. I would like to finish also to thanks and to acknowledge Professor Andrei Silnikov, who gave me really fruitful advices during this work on Muthuswamy-Chua Ginoux system. Thank you very much for your attention.
Thank you very much, Jean-Marc, for this nice talk. So it's nice to see that there is a real circuit, that you find a real circuit which shows all these behaviors. So, any questions? Juan, you want to ask a question?
Yes.
Please unmute. Okay.
Okay. I would like to know if you foresee any applications of this memristor, like, for example, in neural networks or in artificial intelligence.
Not for instance. During the process of publication, we have investigated to find a real thermistor, and we have been in contact with the industrial society called TDK, which is building a real memory store and thermistor. And so we had a real thermistor to verify that this circuit is not only abstract, just an abstraction, but a real circuit. But for instance, we had no application.
Thank you.
Thank you.
Any other question? Otherwise, it's perfect.